Okay, good morning, good day to everyone. So this is Hao Zhu. I'm a social professor of electrical engineering at UT Austin. Together with Dr. Ming-Song Kao, we host the Data Center AI Load Integration Task Force. We have monthly webinar. And today we are very grateful to have two excellent speakers. Before we get started, I want to share a few announcements. We will be at the general meeting next month in Montreal. With this timeline, so we won't have a webinar next month, but we hope to see you there at Montreal. So there are a couple of events that are very relevant to our task force. So we encourage you all to come over to these meetings and the panels events. First of all, that we have a task force committee meeting, and this is Monday afternoon. So please come to share with us. I also get personal emails like what will be the end outcomes of the task force. So let's have a group discussion there to come up with a plan with technical publication and other things. So yeah, look forward to seeing you there. And there are also two related panels, one from SBLC and the other one from PIC, the Education Committee. And the first one proposed by our task force. So there are speakers from industry, academia on this topic. And the second one also have two speakers from Dominion and ERCOT also discuss the data center integration with some education or workforce components. So I think both are very exciting. Finally, I think PES general meeting this year starts this so-called thematic paper session, which wants to highlight a group of papers that are very relevant to timely topic. So fortunately, SBLC, the committee for the Dali task force, has co-hosted a paper session with Dynamic Performance Committee. And actually, I think Ming-Song has a paper in this final Thursday thematic paper session as well. So yeah, please come if you're interested in any of these topics. Yeah, I think that's all from me, and I will hand over to Ming-Song for introducing our speakers.
Yeah, and the presentation of today's multiple theme is integrating large AI data centers, transmission planning challenges, and personal interaction risks. And we have two speakers, including Michael from American Transmission Company and Novan from Hitachi Energy. And Michael is a consulting principal engineer in ATC, and he has an experience in the industry for more than 17 years. And he has background in power quality, protection, stability, and transient analysis. And he received the bachelor's degree from the University of Notre Dame and master's degree from Purdue University, as well as the University of Minnesota. And Nuban is also a senior consultant at Dutch Energy and has more than 8 years of experience. And his experience encompasses the broad areas such as the steady-state analysis, dynamic stability, subsynchronous oscillation, and power quality analysis. And he received his bachelor's degree from Bandung Institute of Technology and master degree from Cornell University. So I'd like to hand it over to Michael and Novan.
Yeah,
Hey,
I
good
can share
afternoon.
my screen. Mike, I can
Okay,
share
you're
my
gonna show.
screen.
Okay, no one's gonna share your screen, and I'll
Mhm.
just my slides there.
Sure.
Let's see.
Can you all see my screen?
Yeah, we can see your screen.
Okay, great. Go ahead, Mike.
Yeah, when you're doing that introduction, I actually started working 40 years ago for Minnesota Power in Duluth, Minnesota, and we had I think our total load at that time was 1.2 gigawatts, our peak load, but we had some very large iron mine loads, so probably in the couple hundred megawatt load for the biggest load, and now we're looking at meg loads in the gigawatt, so it's a different world. I guess it's been 40 years, so. But ATC, let me go. You can go to the next slide there, Novan. Yeah, ATC, we are the basically the transmission only utility in the eastern, I'd say 2/3 of Wisconsin, plus the upper Prince of Michigan. We have a little bit if you look down at the bottom, a little bit in Illinois, and we poke a little bit in the Northwest, a little bit in Minnesota. So our management likes to say we're in 4 states, but we're really basically 2 states. Um, we have more than 10,000 miles of transmission line. Anything above 69 kV, we consider transmission. When we were formed about 25 years ago, out of the utilities in Wisconsin and Northern Michigan, um, the idea was we'd be a small company, maybe 100 people. And the idea was that we would basically get the transmission systems to cooperate because they were kind of going past each other without connecting and kind of not being very efficient. So we were thinking, I think our original CEO said we only have 100 employees. We're up to 650 with all the expansion going on in the grid. We have a HVDC up at Mackinac, which is kind of the northeast part of Michigan there between the upper and lower peninsula. We don't show the lower peninsula here. We have a SVC in kind of the northern Wisconsin area, and we just put in StatCom. We have a couple small StatComs in the upper peninsula of Michigan to kind of help with flow issues. And then we do have a larger StatCom just went into service at a data center down in the Milwaukee, just south of Milwaukee in Mount Pleasant, which they announced yesterday or a couple days ago that that data center is now the world's largest supercomputer. That it's a Microsoft facility, and Microsoft said that, so we'll believe their vice president, and it's going to be a lot bigger. We've I don't know if I can say specifically what their size is, and it does change, but you've heard in the media about data centers in the multiple gigawatts level, and that's kind of where they're heading. But our system, the kind of, I don't say unique thing about it is, but in the southeast corner here, we're between Milwaukee and Chicago and Illinois. It's a very strong system. If you go up the northeast part of Michigan, it's a very weak system, especially northwest part of Michigan. There's very little there, so it's a quite diverse system. Go to the next slide, Novan. So the first time we heard about these gigawatt level data centers was in January 2023. We had well, I can say it's Microsoft because they're operating now. They came to us and said we want to put in this AI data center. We've got this variable load, and someone called me up from our load interconnection people and said, "Is this going to be an issue?" And I said, "Boy, I've never seen anything that varied, hundreds of megawatts multiple times a second or on the range of a second or so." So I called some industry experts, and they all said, "Boy, I've never heard of that." And maybe I've heard something about that, but this was kind of totally new in January 23. So we quickly thought about, okay, what issues could come? Variable load, we instantly thought of flicker, but after a little thought, we thought, well, we got inter-area oscillations, generator shaft torsional oscillations, and just the size of the load. What happens if you lose a gigawatt all of a sudden? Now we're thinking, well, what's a NERC reportable event if you lose so much load? You're thinking of, when you think about that, you were thinking, okay, in a large area. Now, what if you lose that much load at a single point? That's going to have issues on your system. And also the power factor. Our first thought was, okay, if they're consuming a lot of VARs, we're going to have to worry, we're going to have to put a lot of compensation. But then they were telling us, well, it might actually put some VARs on the system. So we're, okay, how do you deal with all this VAR flow issues? Go to the next slide. So the first thing we said, okay, we're going to have to do our typical studies, but just on a much larger scale. Instead of looking at maybe 20 megawatts, we're looking at a gigawatt. So power flow, we have to look at our demand forecast, what kind of infrastructure you need. We don't do generation, we do lines, but we keep asking our generating utilities, where's this power going to come from? Because we're going to have to do load flows that show power going to this data center, and where's it going to come from? One of our fears is that we'll say, well, we'll get all our power from Illinois, and Illinois has got their own data centers saying we'll get all our power from Wisconsin. So we're not directly involved in that, but we're working with our generating utilities to figure out where's it going to come from. And how does it come in? It's hard to get generation quickly. There are some things you can do to speed things up, but we're kind of all operating at our limits. And once we talk about real power, then we had to look at reactive power. Does that have to be static? Go ahead. Do I have a question? if the reactive power, can it be static or do we need dynamic? And this is a very good question because we we kind of had some guidelines for when do you need something like a StatCom, but we don't really have solid rules. And we're forming those rules now because when you go to your commission and say, hey, we need a 350 megawatt StatCom, it's going to cost this many millions of dollars. They're going to ask questions about that. Do you really need that? Can you get away with just switch capacitors? Can you do some fast switching with capacitors? So we're looking at that and we're getting a little bit, again, the power factor question. Are they putting VARs on the system? Are they consuming VARs? How many? We had some, requirements for loads, but they were pretty, they weren't very strict and they weren't very tight. I think it was 0.95 power factor for the load. And that, that's one thing when you've got 20 megawatts, another thing when you've got, a gigawatt. Then the big thing is project scheduling and regulations. Okay, the lead times on equipment are just crazy right now. And the data centers, they have a lot of money and they're used to doing things fast. So they can, in some cases, they can go faster than the utility, depending on what you need to upgrade. If you have to put in some large lines, that doesn't happen very quickly. And we were lucky. The first data center we're putting in, that was a spot that we were going to have a large manufacturer go there, and never they never reached the level they thought they would reach as far as load. So there was some space available there as far as we had some capacity. We had to build a lot more capacity, but at least the basic infrastructure was there. I'll go to the next slide. We also have, special studies. There are some special studies we already do. If there's a issue, we do harmonics. Inner harmonics, we don't so much study, but we just kind of make the customer aware that there in parts of our system, especially near our HVDC, there was a communication system that used the actual utility wires to send signals on. And if you put inner harmonics on a system, that kind of interferes with those communication systems. So we had some experience with inner harmonics. Those types of systems aren't used very much where there's in urban areas. In rural areas where you don't have cellular as available, they're more common. But so inner harmonics not a big issue, but something we always consider. Then, of course, our usual stability concerns, voltage stability, frequency, angular, and control interaction with converters. But we also need to create a special process for a new process for ramp rates. Okay, you can't put a gigawatt on your system instantly. You need to ramp that up and ramp it down if at all possible. If there's, certain contingencies, you may not be able to do that, but you certainly want to limit those potential contingencies. So we have to come up with some rules or some limits for ramp rates, then for load rejection, ride through, when can they be allowed to trip or when is tripping acceptable? You don't want to trip at all, but if you get to zero voltage for a long time, they're going to go off. Then how fast can they return to service in the frequency limits? And the load variability, this is kind of the big one because of 0 to 5 hertz, you can have inner area oscillations, but the real thing that kind of scares us is this kind of 5 to 59 hertz where you can kind of get into the torsional interaction with generators. And from experience with series capacitors, if you get if you resonate with your generator torsionals, in the worst case, you can fail that generator. You can break that shaft. And that is something that no one wants to happen because that's not a 1 month fix or something. That's very expensive, very long term. So that I think we kind of focused as this is our critical thing that can go wrong, the thing that can happen where we don't have a lot of time to react. And that's what Novan's going to talk a lot about. We can go on to the next slide. So for existing criteria, basically for harmonics and flicker, there are IEEE standards, 519 for harmonics, everyone knows about it, flicker 1453. We also, a little bit about the harmonics, the way we have IEEE 519 and our criteria is set up that the load or the customer is responsible for the current harmonics and the utility takes responsibility for the voltage harmonics. And that's kind of important because when we're looking at our system, we've done some simulations. It's kind of difficult to simulate the background harmonics. What we found with the data centers we've looked at in detail so far is that we don't see a harmonic problem from the data centers. We see a harmonic problem when we add capacitors to support the data center. Those capacitors resonate with the background harmonics. And we're not, it's difficult to model background harmonics, so we're kind of waiting till we get something going where we can actually see how much the effect of those capacitors are. It's also a little tricky because the capacitors that we're looking at putting in service are basically only needed for contingencies. So at the kind of the typical level, we don't see any harmonic resonance in the models, but if we start modeling contingencies and we put more capacitors in, then we start seeing harmonics exceeding the limits. Not by a whole lot, but they're enough to be concerned. The problem is in the real system, you can't have your operators take a contingency and throw in a bunch of capacitors to test your theory about harmonic resonance. So we're kind of waiting for an opportunity to put in a bunch of capacitors and see what happens. The capacitors are installed. We just haven't, I think we've had one or two. There's about six we're worried about. And I think the most we've had in is two. We don't really start to see problems till like five of them are in. So harmonic's not a big issue, but we're we're somewhat wary about it. Just you put a large load there that's a lot of electronics, you think there's going to be some harmonics. Flicker, we when we look at those initial load variability numbers in the hundreds of megawatts, you start worrying about flicker. But when you start worrying about the oscillations, the torsional interaction, you're going to have to limit them to much lower load variability, and that kind of takes care of the flicker issue. The interharmonics, we have a limit based on our experience near the HVDC, but it's kind of an informal limit. It's like I think it's 0.4% total interharmonic distortion for the first through the 15th interharmonic, but it's not an industry limit. It's kind of based on our experience, and it's worked so far, but I don't want to put any guarantees on that. Next slide. So the first thing we came up with new was power factor requirements. Our old limit was kind of 0.85, you can see at the left, 0.95 lagging when the load is 85% of maximum forecast. We measure at the load side of the distribution transformer. And now with the large loads, and we define a large load as anything greater than 200 megawatts, although a lot of places have something a lot smaller than that. And for those, we have to have their power factors has to be greater than 98% at the low side of the distribution transformer. Like distribution transformers 138 to 24.9, something like that. It's not a small transformer. So the idea is that we're kind of making the system, putting a little bit more of the requirements on the load. So we will work with they try to be more fair and with the cost control, so we're not basically adding a cost for other customers due to one large load. But we'll certainly work with the customers to coordinate their reactive power design. Do the next slide. So since there was no existing really load criteria for ride through or for load variability, we kind of had to make our own, and we based our ride through criteria kind of on the generator ride through criteria. That's on the right. There is our criteria. I've seen plots where people have all the different ride through criteria, and they're all pretty similar, but not really exact. The other thing we had to come up with was a ramp rate. We came up with a ramp rate of 0.5 megawatts per second, or 30 megawatts per minute. It's I think everyone else puts it in minutes. We'll probably end up changing that soon too. And that's based on, how our system operators, they continually run load flows looking at the next outage. Well, if your load is changing too quickly, those load flows I think they do every 5 minutes or something, become pretty meaningless. So we kind of put a limit on there so that they can keep a good view of what's happening on the system for the next N-1 event. For the restoration, right now we're doing that case by case, how soon they can come back and how do they have to ramp back up when they go out. And it's not something we have a lot of experience with, but we're kind of doing that case by case now. That maybe some more criteria in the future. The big one here that a lot of Novan's going to talk about this is where he came up with our load variability limits. Well, first that ramp rate, if you look at zero point 0.5 megawatts per second, that doesn't kick in until you do 50 megawatts. So that basically I took that box there. If we do 100 seconds, that's 50 megawatts. So that red box is kind of, let's say it's 50 megawatts high and 100 seconds long. So if you're in to meet our ramp rate criteria, you have to be kind of inside that red box there. So the yellow box is kind of for our so that red box is for the ramp rate. The yellow box drawn there, that's 25 megawatts high and 5 seconds wide. That's kind of our oscillation criteria. And you're going to get some more from Novan on how we came up with that. But the idea behind that is that'll keep the oscillations small enough and at a low enough frequency where they're not going to cause an issue with generators. And I'm going to just kind of skip a little over that because Novan's going to fill you in through on that. We also have frequency ride through voltage change requirements and a lot of requirements on modeling. We want good modeling so we can study this. Next slide. And that's kind of the other big thing is monitoring. How do you, okay, we come with this criteria. Our regular metering doesn't look at things like oscillation, frequency, and magnitude. So we're coming up with new protection schemes and also monitoring schemes. We're working with the SEL on doing some of that, and a lot of it is going through our distribution utility, Wisconsin or We Energies, because they actually own they're actually their customer. We Energies is our customer, and Microsoft or the large data centers are We Energies customers. We also have other distribution providers who are getting large loads, so we're working with them as well. The protection action right now, we're trying to set it up so that the load kind of gets the first indication that something needs to be done so they can take some action, either changing their process or dropping some load to avoid the oscillations. If that doesn't work, the utility, which will be We Energies, can open breakers to reduce the load and the variability. At last resort, where they're putting protection on their generators. I don't think right now the generators are set up to trip. I think they're just set for monitoring. After they get some experience, they will probably set that to tripping. I think there is one more slide. And this is just kind of our criteria. It's all available out there online. The planning criteria, probably the best way to go that is to go to the Mid-Continent ISO, MISO. Our latest version is out there. It's usually also out on our website. Sometimes MISO gets updated before our own website because that's a compliance requirement. If you go to MISO's website and look for ATC planning criteria, it'll pop right up. And we also have a load interconnection guide. If you Google ATC load interconnection guide, you'll get to our system, our website, and it'll have the interconnection guide there. And I believe also this large load criteria confirmation form is out there too, if you Google it. Basically, all this is it kind of goes through our requirements and asks the load to kind of say that they meet the requirements. And you kind of require that before we'll let them do much of anything on our system. They're basically, it's to make sure they're aware of what these requirements are, and if they don't meet them, they could be a risk to the system, and that could cause us to take their load off. We don't like to think about that, but that's kind of the ultimate. If your load has a potential for risking for harming other customers, we will not allow them to connect or continue to operate. I think that's my last slide. If anyone has any questions, or do you want to, Novan, you want to start and we'll just do questions at the end?
I think there may be a question earlier. Mohammed, would you like to, Mohammadi? Okay, maybe he's not there now, but I do have a question if you could go back. Okay, yeah, there is a question. Samia, please go ahead. Please unmute yourself. Go ahead.
Hello. I wanted to ask, this is mostly out of interest. What exactly was your reaction when you first heard about the new data center that had gigawatt requirements? Because you said that it hadn't really been seen before. So were you like excited to work on the project or
We uh we called like the smartest consultants we work with, and first thing was what do we do? Is this load variability a problem, and how do we solve it? And I think generally I think we were more excited to do it when we thought there would be one of them. Now that there's, a handful of them scattering around our system, it's kind of becoming overwhelming. But I think a lot of when the issues came up, I think the loads, the data centers said, okay, yeah, it's no problem. Go ahead and fix it. Then we came back and said, okay, this is what it'll cost to fix it. And they said, well, we'll look into fixing it. And they've done a lot to kind of smooth out those loads, yeah, at the chip level. So I think a lot of this we're doing to worry about this should disappear in 5 to 10 years, but it's going to be here for a while. So I think it'll be a pretty exciting 5 years.
okay, thank you.
Yeah, I also have a question on slide 8, where you showed earlier the kind of variability there. Um, so um, so you mentioned that the subsignals, the SSO range is probably of higher concern. So I'm just curious, like what type of time scale have been observed at a grade level from the data center interface from your side? Yeah.
Oh, yeah, but what frequencies?
Yeah, what
Or
kind of range of dynamics have been observed and then have like been shown up some impact to your system?
Mhm. They haven't run a lot of larger AI stuff yet. We've monitored a few times where we've caught them, I think, doing some testing, and it's kind of the magnitudes so far have been pretty small. But I think the generators reported that any variability they've seen that has been repetitive has been less than a megawatt at a 500 megawatt generator. So it's pretty far so far, but they haven't really hit their peak load yet. They're maybe, I'd say probably the loads we've seen maybe a third of what they've told us the peak will be, and they haven't done a whole lot of AI training. So a lot of these plots are things that they've done in test labs.
Hmm.
But
Yeah.
the one question we keep asking him is what frequency and how long can you be at that frequency? And they can't really tell us. Apparently, it depends on the job they're doing. That can vary quite a bit. I mean, if they could say, well, we'll never be at a single frequency more than, 10 seconds, and then we'll move on to a different frequency. That's a lot different than saying, hey, we can get a single frequency and stay there for, a week or something. And if that frequency is a resonant frequency for the generator, we're in a lot of trouble. So,
Yeah, that's really of a concern. Yeah. Okay, thank you for clarifying. Yeah.
Yeah, I also had a very quick question. So I think for our side, we did not consider about the reactive power consumption of the data center mostly. So I just wonder, according to the fluctuation of the active power, the reactive power also fluctuates, or the consumption of the reactive power are more or less constant compared to the active power?
yeah, I haven't looked at the at that as closely. We do have a statcom going in there um, to kind of, if it does vary, to kind of take care of the voltage issues. But I haven't got any really good data on that. But I assume it's going to vary as well. I mean, j just the change in flows through the system, you're going to get different VAR consumption on your lines and stuff. So we fully expect to see, highly varying VARs as well as megawatts. But that's something good. I probably need to look at that more. See when we've been concentrating a lot on megawatts because that's something that's kind of the primary concern right now. But I'm sure the megavars vary as well.
Yeah, that's great to know. Thank you. Maybe we can move on to Novan and come back for
Uh,
questions.
Okay, okay. I have a question. I will leave it later. Yeah.
Oh, okay. Yeah. Thank you.
Yeah, thanks, Mike, for your presentation. I think it has nicely captured some introductions before we transition to my presentation. So um, I'm going to share some experience that we have done in this space, especially focusing on the phenomena that Mike has also already briefly mentioned before, related to the impact of the impact of the AI load on a nearby generator. And I personally would prefer to call this phenomena as a cyclical load-driven torsional interaction. And this is due to the fact that our study here is focused on evaluating the impact of these forced oscillations coming from the AI load oscillations. So as we know, AI loads are known to have significant variable portions compared to traditional data center loads, and these variations would create variations in the electrical demand on the grid. And when we have multiple generators, to the generators, this load variations would appear as a change in electrical torque. And then this electrical torque change, would then get translated into a change in mechanical torque. Now, these pictures on the right just show a simplified, diagram of a generic turbine generator system. But the key message that I want to share here is that a turbine generator shaft is not just one rigid piece. It is actually made of several rotating masses, and these masses are connected by flexible shaft sections. And each shaft section here would have different characteristics. It would have different stiffness, different damping characteristics, and so on. So when a generator experiences a change in electrical torque, that torque change would be transmitted into the shaft, the entire shaft train. And when in the context of AI load, when the load has an oscillation component that is close to one of these generator torsional frequencies, these shaft sections could be twisting back and forth more strongly. So that's the interaction phenomena or oscillation phenomena that is the focus of the study that we did. So we also noticed from this study, like this is a high-level summary of findings that we found from our study, that when such load variations happen, depending on these various factors like the load magnitude, the oscillation frequency, and how long they last, and how closely they are coupled with the generator, how closely the data center load is coupled. These repeated twists could stress the shaft and amplify the potential torque oscillations. So in the worst case scenario, if such scenario happens in infinite time, it could even damage the shaft. Now, I'm going to jump straight to the specific case study. So for context, we have an AI data center load interconnection, and this is a 500 plus megawatt total facility load for the purpose of this study, even though, like Mike said, it's probably going to be evolving in this in the ATC region, the growth of large loads and data centers. And in this particular data center, we are looking for up to 200 megawatt variable load. And we were also aware that the data center load operates at this specific frequency range, which we define as the possible oscillation frequency range from 0.1 to 20 hertz. Now, we also have multiple generators located a few buses away, close to this data center load. And one of the closest generators is a large-scale coal-fired power plant. The big question that we want to answer from this study is that how bad can it be when a generator is continuously disturbed by this cyclical load? So this slide shows a high-level summary of how we approach doing the study. So we first start with gathering the required data that we gather together with ATC and the generator owners, the data center load its owner. And starting with the system data, we first perform a screening analysis. This screening analysis is essentially just a preliminary risk assessment, which aims to basically identify and screen for the closest generators, and also to help us determine the critical contingency or outage scenarios that may yield to the an increased interaction likelihood of interaction between the generator and the load. So we adapt this UIF screening method, which we learn from this EPRI report. This method is originally developed for evaluating interactions between HVDC and fax device, for example, like STATCOM, SVCs, and active devices within the grid. But we use this method and adapt it to evaluate interaction between data center load and a generator. And then once we have shortlisted the generators, we would narrow down and put our focus on specific generators that are appear to have the highest likelihood of interaction with the data center load. Now in this next few slides, I'm going to share specifically our case study on one specific generator, which is one of the shortlisted generators we have from the screening analysis. So we built the EMT models considering the network model from ATC, the detailed generator model, and also the data center load. And then we perform load oscillation simulations, monitoring the shaft torques of this particular generator. And then we compare the resulting simulation torques with the SN curves, which we also got from the generator OEM. And for a quick note, an SN curve is essentially a graph that tells us, the magnitude of stress against the number of cycles that the generator shaft can essentially withstand before the shaft breaks, or before potential problems occur on the shaft. Now, this shows the generator model that we consider in the study. So it's essentially a 4-mass generator model, including the generator mass. And here, the key findings here is that we know that the generator has 3 subsynchronous torsional modes, so 16, 29, and 41 hertz. And then we also know that the most dominant torque oscillations on the shaft appear specifically on the 16 hertz and the 29 hertz torsional modes. And these are the 2 modes where we observe that the torque oscillations appear more significant when the generator is exposed by a disturbance. Now, what we did next is that we focus on one of those modes, and we tune the load data center load model such that the oscillations would align with the one of those modes, which is here 16 hertz is the one that we want to focus in this study. And then considering this approach, we are aware that this is the most conservative way of modeling the load, but the main objective of this exercise is to know how bad can it be for the generator if such generator is exposed to this kind of persistent load oscillations right at the mode. So the next one here is essentially what we observe from our simulations. So on the left side, the plot essentially shows how the generator shaft torque responses under different contingency scenarios. So I think I mentioned before that from the UIF screening, one of the goals was to identify the critical outage scenarios or contingency scenarios that may yield to increased radiality between the generator and the load. And we took those like a selected scenarios from those list of contingencies from n-0 to n-12, which is very pessimistic and conservative. And we simulate this load oscillations and see how these load oscillations could affect the torsional response of the generator. Then on the right side here, I am showing 3 small plots of SN curves particularly for one of the shaft segment. That is the shaft segment which we found to be the most significantly affected shaft. And here we have plotted the resulting simulation torques against the SN curves, considering the 3 outage scenarios that we simulated. And overall, the key findings from these plots is that increased radiality and therefore reduced network strength leads to more amplified torque oscillations and potential fatigue limit violations. As we see here, from the left to right on these 3 SN curves, we can see that the more radial the network, between the generator and the load, and the weaker the network is from the point of interconnection of the data center, the resulting violation becomes more severe because the torque oscillations also become greater and more amplified. And then the second key finding here is that if we reduce the magnitude of these load oscillations, it could potentially reach to a point where we could mitigate the potential violation. And here we can see that, for example, on the first Hassan curve here, we can see that if the load oscillations go at this magnitude, 80 megawatt magnitude, it may mitigate the issue. It may bring the torque below the violation limit. But when the network is weaker, the limit may be different. Here we can see that under n-5 scenario, we would need to bring the load oscillations even lower to 40 megawatt to bring this torque oscillations below the endurance limit of the SN curves. So this is one case study that we did, and then the next one is what happens when the load frequency doesn't align with the generator modes. So we did a sensitivity analysis here to show that if the load oscillation frequency deviates around the torsional mode, how would it be? Now, it really depends, like how close the load oscillation goes, towards the torsional mode, would really influence the severity of the torque oscillations. And we can see here that as we vary the randomness of the frequency around the mode, increasing the standard deviation of the frequency around this mode would make the torque oscillations less severe or less scary compared to the base case scenario where we assume the most conservative approach. So the key findings here is that if the difference is significant, well, it may not be an issue. But the closer they align the oscillations with the mode, then the greater the potential for torque amplification. Now, the next few slides, I have a couple more slides showing how different potential mitigation solutions can be applied to mitigate the risk. But essentially, we are aware that many industries are exploring ways and doing heavy research on how we could solve these AI load oscillations. So there are two potential mitigation strategies that I highlight here. The first one is load smoothing technologies. As we know, eStatCom, BESS, and like Mike said, even rack level or GPU level smoothing solutions are also one of the emerging technologies that are currently being explored. And maybe in 5 years, maybe we would not see the same problem. Maybe these oscillations would not be relevant anymore. And then the second one is the coordinated protections and monitoring between the generators and the loads. And this is also one of the things that Mike mentioned. That is also one of the ongoing work that ATC is doing to protect the generator and the load. We ran some simulations using eStatCom and BESS here, just to show an example of how mitigating the oscillations at the high voltage level or the medium voltage level could also potentially solve or mitigate the risk. And here is essentially an example of how coordination between BESS and eStatCom could be capable of damping the oscillations at a specific critical frequency that we want, and significantly reducing the torque amplification. But we also note here that we are aware that proper tuning and coordination between both devices would be really important. This particular plot, doesn't represent any specific product or brand, but just to serve an example of how these different devices can be leveraged. And then we also, perform an exercise using the nerve profile, and to see how these BESS and eStatCom devices could be coordinated and used to smooth the load oscillations. We are aware that the real AI load profiles may contain multiple frequency components, right? It may not be as conservative as what we have considered in the study. But and this is just to show like a more realistic example of how these technologies could be leveraged to damp the multiple frequency components inherent in the load. And then some key takeaways, as we know, sustained load oscillations, when they coincide with the generator modes, they could excite amplifications, and if they are undamped, that can lead to failure of the shaft. And then some influencing factors that I described before, like load oscillation frequency, the closeness to the mode, the magnitude of the variable load, the duration of the when those load oscillations appear, and also the radiality between the generator and the load. Those are some influencing factors that could really determine the severity of the issues that we're looking at. And potential mitigation strategies, I'm not going to repeat because we just had discussed this before, like coordinated protections, load smoothing technologies. But essentially, the developing a proper mitigation strategy would really require close collaboration between utility or TSO, data center, and generator owners. And I think this is my last slide. These are just some recommendations for future work and research, and I'm really happy to for any inputs or any feedback from the group as well. But in my opinion, I think there are three aspects or three areas where I think would be an interesting topic for future work and research. First one is screening methods. As we know, detailed PSCAT or EMT studies are very resource intensive. They require a lot of time and resource, and I just think that developing efficient screening approaches without the need for extensive modeling in EMT, as long as it can provide like credible risk assessment, that would be really helpful, and that can really help TSOs or planners identify generator risks early, more efficiently, and also guide how they should plan their mitigation strategies. And then the second one here, alternative risk assessment methods to S-N curves. What we observed from this project is that S-N curve is not always available, and it's really difficult to obtain from OEMs. We were just lucky enough that we could manage to get an S-N curve from one of the generator owners. But I think alternative methods to kind of credibly assess the fatigue risk for those generators and also help us define the allowable load limits. This is an interesting area of work and research that I think could be considered for future industry or academic research. And then the last one, load smoothing solutions. Like I say, several technologies can mitigate load oscillations, but I think further study can be done to to see how these different solutions from rack level, GPU level, low voltage, high voltage, how they can all be coordinated to further optimize the overall solutions and also the overall mitigation strategies for TSOs and data centers. So I think that's all I had. Um, I'm open to any questions the group may have. Thank you.
Thank you for the nice presentation and very insightful discussions. Yeah, thank you both for the excellent talks. Yeah, so we will open up for questions, and please, if you can raise your hand, and we will go through each question in order. Yes, Samuel, please go ahead.
Hello. I wanted to ask a question about the voltage solutions for load smoothing. Have you considered what application solar power could have in that field?
Sorry, solar power?
Yeah, for the load smoothing, you have rack level, low voltage, and high voltage solutions. Do you think solar power could fit in there in any sense?
Um, I haven't done any study to evaluate how solar power, or by solar power you mean solar PV plant collocated with the data center load. Is that what you're referring, Samir?
Yes.
Yeah, I haven't particularly done study involving, how solar power can be used to mitigate load oscillations. Um, yeah, I don't know if we have any PV plant, like real PV plant collocated with a data center load yet. I haven't heard. Um, maybe maybe the group or maybe Mike, if you have any insight into this within the ATC territory, have you heard of any?
We do have some solar nearby. They're not co-located
Mhm,
with the large loads, but you could see how they might want to use solar to kind of charge a battery and kind of use that
mhm,
for some damping. Our concern is, control interaction between the data center and the solar. Right? I don't think it's a huge concern in the sense that it can't be fixed if you see something like that. These controls seem very flexible, so if you if you study them well, you should be able to avoid any negative interaction. But
mhm,
um, so we're kind of looking at that for IBRs near our large data center loads. But I we haven't got any collating locating yet. I part of it might just be they're trying to do everything so fast. They don't have time to worry to think about that yet. They're too busy trying to get them up and running.
mm.
All right, thank you.
Okay, thank you.
Thank you, Mike.
And Jay Wang, did you want to ask the question earlier?
Yes, I was planning to ask a question regarding the protection. I see Michael and Novan had both mentioned protection, and they both look at from the inside of the data center. For example, how to protect the generators, etc. So I'm taking a different aspect perspective. So I'm wondering from the transmission grid operator or ISO utility perspective, are there any real world events or any research have shown the problem of data center, the challenge of the data center bring to the protections. Um, any data center, those kind of very fluctuated load and also the RESU capabilities, how will that impact the transmission protection? Yeah, from the grid side, not from the data center perspective. Yeah.
Mm,
Yeah, I think that's a good question. We've got all of a sudden something, strange happening on the system. Will, the protection that's already out there misinterpret that as, as some kind of event where it has to operate? I think the modern relays are pretty good at kind of filtering out things they shouldn't be seeing. But especially if you get, as things I'm thinking like harmonics and um, things like that. But we haven't really I'm not a protection engineer, so our protection people haven't come to us with any particular concerns. So I don't think there's anything that we know about yet, but there's always surprises and things. One thing that when we do talk about protecting the generators, we put these torsional shaft relays on there. Some generators, are built with ways that you can monitor that fairly easy. I'm not saying I shouldn't say easy, but they're built so that you can put monitors on there. And other ones, if they don't have that, it becomes really difficult to retrofit it. So protecting the generators can be, I don't want to say easy, but more doable for some generators than others.
Okay, good to know. Yeah. Thanks for the information. Yeah. Looks like the focus and the challenge is more on in the generator side, not from the transmission side yet. Yeah. Okay. Thank you. Yeah.
Yeah, what an interesting thing about the plots that when Novan showed that if the way he studied it is, you're right at that resonant frequency, and still it takes some time to build up to get to the point where you're violating the SN curve. But the reason the reason we were able to do this is because we were able to get the SN curve for a large nearby generator. It is like it's worse than trying to pulling teeth to try to get this information out of the generator manufacturers. These SN curves. I think they're just concerned that we might be reading too much into them, because I've talked to some generator manufacturers at IEEE meetings and things, and they kind of caution that these SN curves are basically built for the shaft. There's other things in the generator that could have issues with variable load, which can lead to vibrations. So I think part of it is they don't want to put these out there and represent them as, if you match this, everything's going to be fine, because there are other things in the generator that might be issues, even though they may not be the shaft, but just whenever you rattle a large piece of equipment, you have potential for things to wear out sooner, or shorten the life and things like that. This method of doing the analysis, I think it's very good, because you're actually looking at some actual data on that generator, but it's very hard to get these SN curves out of people. So there's other methods looking at what's an acceptable load variability that make some assumptions, but we're making a lot of assumptions here as well. But we're basically starting from something that actually represents a real generator, the SN curves here. So there's a lot of assumptions in this, but there's other methodologies that also use a lot of assumptions. And I would say these assumptions mostly are very conservative, but that's kind of what utilities are like. We build things to last for 30, 50, 100 years. We don't like to take a lot of risks.
It's true.
Yeah,
Yeah.
great point.
Thank you. Yeah.
Great. Thank you for the question. Mohammed Madali, yeah, please.
My question is about slide 18. Am I audible? Sorry. Am I coming through okay now?
Yes, we can hear you, and yeah, we're seeing slide 18.
It's about slide 8.
8, yes. Okay. I
21.
think that was
Slide 21.
21?
8,
Yes.
right?
Slide 21.
Oh,
Oh, okay.
Yes. As I see here, you consider the impact of ES SATCOM and BESS together. How did you see the role of BESS in this area?
Yeah. So in this particular example, we tune the best to maintain the active power flow right at the data center POI to a certain magnitude. So as we see here, the magnitude is around 0.6 or 0.7. And that's the the dispatch or the active power flow which we would expect to flow from at the data center POI. So in this case, a BESS is connected in parallel with the data center at the medium voltage bus of the data center, and in that scenario, the oscillations, the reductions of these oscillations would be maintained around that dispatch level. So best role here is to basically control the set point of the active power. But most of the most of the work in reducing the oscillations, as we can see here on the second plot, is really done by the eStatCom in this case. But
Yeah.
this is just an example of how one particular scenario where these devices can be coordinated.
Yeah, so the role of SATCOM is more important than BESS in this area, yeah?
Mhm. For eliminating
Like
the fast oscillations.
oscillations.
Mhm. But I personally think that both devices have the potential, to mitigate fast oscillations. Uh, Maybe with some more proper tuning of each device, the performance could be improved. But here we're basically taking, both eStatCom and best model, and not much of tuning efforts were really performed to improve the performance.
Yeah.
No, I fully agree with you. I think the power electronics advances is gonna help us a lot down the road.
Mhm. Yeah.
Yeah, right now you have the BES for the slower long energy or long or high energy thing, and the eStatCom for the fast things. And depending on what your load variability is, maybe you don't need that much fast, or maybe you don't need that much energy, and maybe you can like tune like Novan mentioned, tuned either the BES or the eStatCom and cover it. So
Mhm.
this is kind of like the um, I want to say the quick way of doing it. But if you have more detail, you might be able to tune it and maybe not need both of them.
Mhm.
Yeah, we have another question from Seoul. Please go ahead.
Yeah, so first of all, yeah, thanks for the nice talk. And I have one question. So could this like torsional stress affect the multiple generators at once through the grid, like rather than just a single unit?
Yeah, I think it's possible. But different generators would have different characteristics, and therefore, they would have different torsional modes or different critical frequencies. So, uh, you know, depends on the frequency components of the AI data center load. If the load oscillations contain multiple frequencies, we that presents some risk to any generators that also have the same frequency components or close frequency components to those loads frequencies. But I think that is still a possible scenario. Uh,
Yeah, I think I did talk to some generator manufacturer a year or so ago and said, well, what they're going to have different resonant frequencies. So if in the worst case scenario, it's going to take out one generator. If you've got protection on all your generators and one sees oscillation, it'll trip that one. The others will be okay. And they said, well, if you've got if you've got multiple generators built at the same time by the same manufacturer with the same ratings, their resonant frequencies are going to be pretty close. So I think it is possible that if you've got that, if if you have multiple generators made at the same time by the same manufacturer with the same rating, they could have the same resonant frequency and trip at the same time. So
Yeah.
Yeah.
I
Thank
think
you.
Jing,
Yeah.
yeah, thank you. I think Jing has more questions. Do you want to ask again directly or?
Yeah, sure. Thanks. Ho. I was wondering, for those mitigation solutions you showed, base and the E-stack home, have you ever considered the double conversion UPS as well? Because that's another type of solution industry have investigated very intensively. Yeah.
Yeah. Yeah. Thanks for the question, Joang. We are aware that new or enhanced UPS technologies, which involve double conversion UPS, is one of the technologies being explored. And
Mm-hmm.
I think there are many companies out there have published their new UPS technologies, where they mention that their UPS could help data centers meet right through criteria, for example, and even damp oscillations right at the close to the rack, right, at the low voltage level or rack level. And we have also explored this in another project that we have ongoing. Uh, and what we found is that depending on the specific limitations of the UPS, uh, it doesn't really eliminate the need for uh, support from BESS. So it may still need some support from uh, the backup battery unit, or even grid level BESS. That's what we found from the study, because the UPS may be able to damp the fast frequency oscillations, in case of in terms of the oscillations. But when you know when for low oscillations, best in one of our use cases, uh, it appears that we would still need best to compensate for this low oscillations, and big jumps between training and idle load, uh, for uh, for maintaining the ramp rate within an acceptable limit. But yeah, I agree that like how Professor say, power electronics, it's a rapidly evolving field, and I think maybe in 1 year, maybe in 2 years, maybe we would find a solution uh, to solve all these problems.
Yeah. Okay. Thanks for the information. I have another question you already mentioned. So can you please comment on the response speed and also the ramp rate of base and the E-stack home strategies?
Yeah, I think this specific question would be better answered by the product expert. Like, I'm not a best or statcom guy, and but from what we study here, uh, here we can see that eStatCom provides faster response than best. And in this case, we can clearly see that to damp the fast 16 hertz oscillations, eStatCom is doing most of the work. But yeah, I cannot really give specific insight into the existing or current technologies that we have in BESS. Maybe there's some ongoing research and development activity going on to improve the performance of BESS, and maybe there's some other ways that we can use when leveraging BESS. I've seen some other papers or articles, where a company is using BESS not in parallel with the data center load, but they're using some inline or series BESS in series with the data center, So there are infinite, I believe, ways to explore how best can be really leveraged. Yeah, I'm really sorry that I couldn't really
That's okay. Thank you. Yeah.
answer the question.
Yeah.
Yeah,
Thank you for
just add a little bit to that. It really depends on what's the rate of change of the load, and little, at first we said, okay, it's a step change, and well, it's not really a step change. There's a little bit of time, and the eStatCom, the BES, and UPS is all, have a different ability to deal with, the fast changing of the load. And it gets really case specific.
Yeah. Mhm.
Agreed. Yeah. Thank you.
So Michael and Noah, as you can tell, there are still a lot of open research questions, and we have a lot of researchers who are really eager to work on this area. We really would appreciate if there are more like open source data or some like public insights that can be shared, so we can build the ecosystem and tackle this challenge. Yeah.
Yeah,
Thank
one of
you.
the challenges, is we go to the data center and say, here's what they give us a load, and then we say, okay, here's how you address that issue, and then they come back and, oh well, we changed it. Now the load looks like this.
Yeah, so
It's like,
that's yeah, okay. If it's not up to date, but still, yeah, any insight is better
yeah,
than
they're, if we could, well, just kind of I don't know if it's, uh, there's one data center you say, well, we need you to solve this load variability problem. We don't want to deal with it. We want you to deal with it. And say, okay, well, we need a BES, we need this, we need this. It'll be $1 billion. And then they go, well, we'll deal with it. Maybe we'll take another look at that. It's-
Yeah, yeah, they have the money. They can do it. Yeah, for
yeah,
sure.
and they're used to operating much faster too. So they
Sure.
their design, I think they go through the new AI chips maybe once or twice a year. They get a new design of those, and they're going to be a little different. And if you say that that they have to flatten the load, they can do that. It may take a couple years to go through some design cycles, but they seem to be making progress.
Yeah. It's great. Yeah, thank you so much for spending the time with us and for sharing this very informative, very insightful presentation. We really appreciate it. So I think with that, yeah, sorry for taking extra time from you guys and also everyone in the audience. But yeah, we are good with the webinar this week, this month. Let's give Michael and Noah another round of applause or virtual applause. Thank you guys for your time. Yeah.
We'll see you in Montreal.
Oh, great. Yeah, yeah. Please come to our task force meeting. And yeah, during our panels and the thematic paper session, yeah, as shown here, we should send out a calendar invite for the task force meeting to every member to the membership list as well. Yeah, but thank you guys so much for coming today, and look forward to more discussions in Montreal. And we should also yeah have more speakers for the webinar. So if anyone is interested yeah, discuss your work or the challenges that you have seen, please email Min Song and me. Yeah, data center data. I guess Mohammed has a final question, but yeah, I will. So do we have your email in the list, or yeah, I guess we can paste your
Yeah.
email
Mm.
or share your email when sending out the webinars
Yeah.
email. Yeah.
As for the data center data, you have to get permission from the customer to release that, because I think that's somewhat of a trade secret for them. But some of it has been released. So, and I think as things go into operation, we'll have more of that data, and there'll be more pressure to release it.
That'd be fantastic.
Thank
Yeah.
you again for hosting the
Yeah.
webinar.
So we will send out more follow-up. Yeah. Thank you. Great. Yeah. Guess that completes our webinar. See you in Montreal.
Take care.
Bye.
Bye.
Bye-bye.
Bye. Thank you.
Yeah, thank you. Bye.